Under normal circumstances, one would expect a 4,500-ton tower of steel to stay where you put it, unless of course this happens. Common experience suggests that objects tend not to fly off the surface of the Earth, and it's because they require energy to do so. In the case of the rocket here, the energy is coming from the enormous amount of fuel being burned by those boosters, and is being converted into what's called gravitational potential energy. In order for an object to move up, it must have gravitational potential energy added to it, and as a consequence, any object that is up must have gravitational potential energy to expend. To illustrate this point, consider what would happen if your children placed a large heavy rock on top of your head. While it's resting there, it's a little weird, but you're in no particular danger. If, however, they were to raise it slightly up, that rock is now charged up with energy and is ready to do some damage. Now don't panic. I can promise you that I'm perfectly fine because no one on this planet trusts my children less than me.
The mathematics behind gravitational potential energy are relatively simple. We are going to require three variables in order to measure gravitational potential energy. The most important thing we need is the mass of the object in question, which we're going to use an m to represent, m for mass, measured in kilograms, as always. The second quantity we need is the acceleration due to gravity on Earth, which we've been using already as a constant, 9.81 meters per second squared. That's its unit because it is an acceleration. And the third thing that we need is the height to which the object has been raised. So we're going to use an h for that. It would be height measured, again, as always, in meters. Now you combine these three things together and you get a reasonably simple equation that the gravitational potential energy of a particular object is its mass multiplied by the local acceleration due to gravity and the height the object has been raised to, all multiplied together. So the most straightforward question we can answer about gravitational potential energy is just how much energy is required to raise a particular object to a particular height. So if we just make up some numbers here, we're going to start with a mass. Suppose you have a mass of 2 kilograms, which is about the size of a typical pumpkin. And we're going to be on Earth, so we're going to use 9.8 meters per second squared as the acceleration due to gravity. And let's suppose we're going to take this pumpkin up to your second floor, which is going to raise it approximately 3 meters above where it was resting on your front porch. Now, what you're doing with the pumpkin on your second floor, I don't know, but you do you. So we're going to start with our equation here, and we're going to have to put in our mass, our acceleration due to gravity, and our height into this particular formula. So if we start with the equation, and we have a mass of 2 kilograms, multiplied by an acceleration of 9.8, raised to a height of 3 meters. If we do this multiplication, 2 times 9.8 is 19.6. And 19.6 multiplied by 3 gives you 58.8 joules for your energy. So in order to raise your 2 kilogram pumpkin 3 meters in the air, it will cost you 58.8 joules of gravitational potential energy. The second type of problem you might be asking yourself is, if I have a particular amount of energy and a particular object that I'm trying to throw, just how far can I throw it upwards under Earth's gravitational field? So we already were talking about your upstairs pumpkin. So if we stick with its mass of 2 kilograms, and we remind ourselves that we're operating on Earth, so our gravitational acceleration will be 9.8 meters per second squared, as always. The question is, how high can we throw this thing if we happen to have 490 joules of gravitational potential energy? So we're going to start with the same equation, and we're going to fill in our mass, our acceleration due to gravity, and our energy, and we're going to have to use some algebra in order to solve for the height. So if we start with that equation, we pre-decided that we're starting with 490 joules worth of energy, and that your upstairs pumpkin has a mass of 2 kilograms. We are still on Earth, so 9.8, and we're trying to figure out how high we can throw that thing in the air with this particular amount of energy. So doing a little bit of arithmetic here, 2 times 9.8 is 19.6. Now we've reached the spot where we are all done with number crunching, so we have to use some algebra. If 19.6 multiplied by the height gives you this number, you can break this with division. So we're going to throw this number to the other side. So the height must be 490 divided by 19.6, and through the magic of having things prepared in advance, I can tell you that the answer to that is 25 meters. So, had you 490 joules to dump into your upstairs pumpkin, you'd be able to throw it 25 meters in the air. The final type of question you can ask yourself about gravitational potential energy is, if I know a particular amount of energy and I know how high I need to throw that object, exactly how much mass can I throw? So if I were to tell you that we started with this particular amount of energy, which is a weird number, but let's just run with it, and we happen to be throwing something under Earth's gravitational field, so we have an acceleration of 9.8 meters per second squared, and we are trying to clear a 10-meter object. Now 10 meters is pretty high. That'll get you clear over a 3-story building if you'd like. Just how much mass are we going to be able to throw using this amount of energy? So if we start with the original equation, as always, in goes your energy, the 7,840 joules. I'm not sure how much mass I can throw, but I know that the gravitational acceleration is 9.8, and the height I'm trying to clear is 10 meters. So 7,840 will be the mass multiplied by 98. And now that I'm done with all the arithmetic, I'm going to have to use some algebra in order to get this 98 over to this side. So I will divide both sides by 98. So whatever this fraction is how much mass I can throw that 10 meters up in the air. And again, through the magic of having everything pre-prepared, I know that 7,840 divided by 98 happens to be 80 kilograms. So, forget throwing pumpkins, now we're throwing full-grown people.
For practice work, more topics and videos, check the website. And to be sure, no middle-aged men were harmed in this film.